calculate the cohomology ring, equivalent cohomology ring of toric manifolds or toric orbifold altogether, and then also derive something about the ordinary cohomology of toric manifolds and talk about what can we do with that cohomology of toric orbifolds too. Okay, and before I start anything, so I have to do, actually my computation is based on the construction of toric manifolds and toric orbifold in terms of polytope. Right? So I'll do that construction in the beginning, but before that, because there will be 3 abelian group hanging around, like 2 torus and maybe some disconnected torus. So let's make sure the notation everybody get it. So say, so T is always going to be m-dimensional torus. Right? So it's isomorphic to U1 to the m. Okay, and then I'm gonna use another torus R. Yeah, R is torus today. It's n-dimensional torus. It's isomorphic to U1m. Okay, and I think in the beginning I'm gonna just set these isomorphism between T and R and T to U1m and R to U1, and I fix the isomorphism. So identify R as this standard torus, T as a standard torus. Okay, and suppose you have a surjective map, yeah, from T to R. And this surjection, I always denote it by B. Okay? And when you have a map from torus to torus, yeah, and that gives you some integral matrix. Is this okay? Yeah? So B actually is a matrix of size n by m, and with an integral value. Yeah? And the way we get this is all the homomorphism from T to R, you can write it as, say, you have Ti, right? This is ith component of this M torus, and it goes to, so you have a matrix, right? And so here I varies from 1 to M, yeah? And I want to get n torus elements. And you have n by m matrix. What you can do is take a product I1 through m, and for ith component you multiply multiple encoded in the matrix. So B, and I think this should be J, I, and J varies from 1 through n. Yeah. So so this matrix B is Bij, right? So I have to flip this I and J because I varies in this notation 1 through n, right? And J varies from 1 through m. Yeah. So for each I, well, maybe I just should use J here, huh? And then Ij, J, wait, I, yeah. So that's how you get the, when you have a homomorphism between torus and you get a matrix, that's how you correspond them one by one. And the surjectivity means what about this matrix B? What's the condition for this map to be surjective? Yeah. So when you have a homomorphism between torus, you can deduce it by taking a differential. It has it gives you a map from Lie algebra to Lie algebra, and I use this frac T and this is frac R. Yeah, this is Rm. This is Rn. Yeah. So I denote this maps on the Lie algebra also by B. Okay? And this is exactly a matrix. Yeah? The weight on this component exactly becomes the entry of the matrix, which is the linear transformation from Rm to Rn. And the surjectivity means that this has to be surjective. So that means this matrix has to be rank n. Yeah? So basically I'm saying there's one-to-one correspondence between surjective homomorphism and this rank n matrix B. Yeah? Okay. So now, right, so you have this matrix B from Rm to Rn, but B is integral matrix because it comes from homomorphism between torus. So you can actually restrict this linear map on the lattice. So for the lattice, I define it as the kernel of the exponential map, right? So it's just a natural lattice sitting inside of Rm. So my torus is just the quotient of Rm by the Zm. Yeah? And this map B is also, this map is also denoted by the matrix B. Okay? All right, so now I want to talk about the kernel of this map. So here, so this is basically the exact sequence, a short exact sequence. G is the kernel of B. Okay, so these are the three abelian groups I use today's lecture, right? But G, sometimes it's not connected. Yeah, so the kernel of a surjective map might be disconnected. Yeah, so maybe I'll do example. The easy one is from Z to Z. Let's look at multiply by 2. So this, in terms of U1 to U1, this map is just T goes to T squared. Yeah, the kernel is Z2. Yeah, it's not connected. So, like you can ask when this G, the kernel of this map, is connected. Yeah? So when you look at this, why you have this disconnected kernel? And this map is surjective, right? So you have a short exact sequence exactly looking like this. Okay? And why this kernel is disconnected? Yeah? And somehow when you go to, this is the, so TZ and this is RZ, right? It's just Z, but, right? And when you go down to these maps on lattice, you don't see the kernel, right? And here you don't see the kernel. But somehow the kernel appears at the level of the torus. And why is that? Yeah, so there's a complete classification of when, determination of when this kernel is disconnected. So here is the, I already gave you a lot of hints here, but the exercise is G is connected if and only if blah. So when you look at this map B at the level of the lattice, this map is not surjective. Yeah? So because this matrix, you're multiplying too. So it's like you have a Z, so this is the target, yeah, RZ. But this TZ goes to only even integers, right? So there is a missing point here. Yeah? So if that kind of thing happens in this level, then as I said, those T and R are the quotient of this T and quotient of T by TZ, quotient of R by RZ, right? You take a, so T is a quotient of this by this, right? But it goes to the quotient of this by this. But then this map is not surjective, so you have to kill more than TZ. So that gives you some kernel in here, which is not the connected part. Does it make sense? Some people say, oh, but not all. But I struggled this a lot, like maybe a couple of months, like when I got into this Toric business. There's no place this people explain this very explicitly. So you have to actually struggle by yourself, like making this sense. Like it becomes all natural after you practice a lot. But so anyway, so G is connected if and only if the image of TZ equal to RZ. Yeah. And this has to do with it has a little bit to do with Delzan condition in a toric manifold. We'll see later. But so we have this equivalence between connectedness and this surjective map at the level of the lattice. Okay? But actually, there's better than this thing happening. Say G1 is the connected component of G to the identity. Well, how can I say? It's a connected component of the identity. Yeah? Identity elements. And G divided by the connected component. So this is the disconnectedness of this abelian group, right? It's isomorphic to RZ modulo B TZ. Yeah. So this is better than this equivalence relation. Yeah. And this you can also find this by thinking of this T and R as a quotient of T by TZ and R by RZ. And you see that what you have to kill after you kill by TZ in this R side will correspond to the disconnected component. Yeah. Okay. Right. Just a matter of notation. Now I have this. So here there's a kernel which is. So this is rank M vector space. This is rank N vector space. There should be a kernel of dimension R M minus N. So this is actually the Lie algebra of G, right? It's the Lie algebra of this connected component to the identity. Yeah? But you don't see the disconnectedness when you look at the Lie algebra. Right? And so here you have exact sequence, and here too. So because this is surjective, you have the short exact sequence at the level of the Lie algebras. But in general, you don't have a short exact sequence at the lattice level. Right? As I said, the co-kernel corresponds to the disconnected of this. So it might exist over there. Yeah? Okay, and usually I denote this map by A. Okay? It's pretty nice, GTR, A and B. Okay, I use this all the time, so like just put in your head from the beginning. Right, and then you have this is the maps induced at the level of the Lie algebra, and you can dualize it. So here you have a B dual. So basically this is a transpose of the matrix B. Yeah? And then you have a trans of the matrix A star. And usually I fix identification of the standard torus at T and R, but sometimes I don't really care about the identification of this G to Rm minus n. So I don't really get I could, but I don't. Sometimes I don't really mention this matrix A. But B is always given explicitly from the polytope. Okay, and we can also do this matrix A and B at the level of the lattice. In this case, this is the dual lattice. Yeah? Okay, so this is just the notation I want to fix once and for all today. Okay, so now let's start constructing a toric manifold and toric orbifold. And basically all the toric Probably, maybe not, but at least in the case of toric manifold, it all comes from reduction of complex M space by some group G. So this R, so we're talking about toric manifold and toric orbifold. So there is some torus acting on it. And that torus is going to be this R. Okay? But actually, we're going to get this toric space as a reduction. So actually, it comes from the larger torus actions. And that will be this T. Yeah? And which group you use to reduce the space, you use G. So you reduce a space with a T action by the group G, so that there's a residual action R, that will be the torus action on the toric manifold and toric orbifold. Yeah, that's the big picture. All right, so let me, So let me start with the combinatorial data we're going to construct toric orbifold and manifold. So today, in my lecture, I don't really care about the classification theorem. My goal is to calculate the cohomology. So I started with the combinatorial data and construct toric manifold and toric orbifold. And then using those data, how can we calculate the cohomology? So that's my goal. So I don't really care about classification. So I start with a pair, delta and B. And it's called labeled polytope. The construction is due to, this is a generalization of Delzan construction. It's due to Lehrman and Tomoo. Yeah? All right, so what is this? So delta sits inside of, you see, R dual. Okay, R dual, it's isomorphic to Rn. Yeah. See, that's where things start. And this is a simple, rational polytope. So when I say polytope, it has to be convex and it's bounded. So it's a nice and pretty polytope. And the simple means that each vertex is exactly the intersection of exactly n facets. The intersection of exactly n facets. So n is the dimension of the polytope. Okay? And so this was the part of the condition in this unimodular polytope. Okay? Unimodular means that it's simple and the normal vectors to each facet giving you a vertex form a basis of n lattice. Right? So it's part of the unimodular, but this doesn't mean it's a unimodular. And here I don't talk about unimodular things because I want to include orbifold too. Right, and the rational, it's the same. Normal vectors are rational. Rational means that those normal vectors can be taken as an integral vector. Yeah? Okay, so maybe I just put a little bit more bounded, convex. Okay, so that's about this delta, a polytope. Yeah, and what is this B? So before that, let me say H1 through Hm, those are the facets. Yeah, M facets. M facets goes here, the dimension of this big torus. Yeah? And for each facet, there's a normal vectors, and I take an inward normal vector, and because it can be integral, I take a shortest integral vector going inward. So rho 1 through rho m is inward integral shortest vector. normal. Okay, and shortest, usually we say it's primitive. Primitive means that if, V equal AB prime implies that A equal plus minus 1. Yeah? V. So say V is an integral vector. A primitive means that if it's with a multiple of some other vectors, the multiplicity has to be plus or minus 1. Yeah. Okay, and this B is some positive integers labeling those facets. B1 through Bn is positive integer. Yeah? It's M. This is N. N. So the dimension of polytope is N. This is the dimension of polytope, and this is the number of facets. Yeah? And I didn't talk about the number of vertices. Yeah? Okay. Right, so now let's get the matrix B. Yeah? So somehow the combinatorial structure behind toric orbifold is here. The polytope gives you a combinatorial structure, but then there is also algebraic information comes in. That's this matrix B. Yeah? So B, you set it to be the B1, so this is the labeling, B1 times row 1, B M times row M. So this is the matrix of size n by m, integral matrix. Okay, so this automatically gives you this short exact sequence, right? It gives you a map from Tm to Rn, yeah? And then there's a kernel, G. Okay, so the G is defined as the kernel of the map from B T to R. Okay, and the inclusion to T, it's given by a map A. Okay, just a notation. All right, so now I have all the data to, not really. So one another thing, some numerical data from the polytope. I need to construct a symplectic structure. So it's a polytope, so it's given by half spaces, intersection of half spaces. So that description in a polytope is given by a bunch of linear inequality, right? So delta is given by, so the U, so U is supposed to be an element of R star. If it satisfies a bunch of linear inequality, okay, there are M inequalities. You know, it's the number of facets. You know, each facet gives you a hyperplane, and then the intersection of half spaces given by those hyperplanes. That's the description of the polytope. And somehow the normalization we are using is here, right? I use like the normal vector to the facets to be bi times rho I. It's the multiple of this primitive inward normal vector. And because of, once you fix this, then there is some number here which gives you the half space. Yeah? So this eta I, it's a vector, right? 1 through m. And this vector I assume it to be in the T dual. Yes, T dual. Okay, and this vector could be just random vector. I mean, it doesn't need to be integral. Yeah, if this vector is integral, then the polytope is actually going to be integral polytope, which means that all the vertices are integral points. Yeah, and that somehow corresponds to the algebraic variety too. Yeah, but if this is rational, it's more like purely symplectic structure. But anyway, those are the numeric data you get from the polytope. So now let's start constructing let's talk about this reduction of complex plane to get the toric space. I like blue, but maybe blue is not really easy to erase. Okay, so let's consider, CM has a standard symplectic structure, and there's a standard torus acting U1M acting on CM. Yeah? And this action is Hamiltonian, and there is a natural moment map going to T dual. Now recall that this U1M is the M torus, right? So there's a standard Hamiltonian action. So there's a standard moment map, and the moment map I use Z goes to the square norm. Yeah, and somehow this fixes the description of the what the Hamiltonian condition is, the plus minus thing, and also there's some 2 pi hanging around when you define a standard symplectic structure, and that this also fixes the standard symplectic structure on CM. But so I hope that this will fix everything before we have this fixes everything we haven't really fixed before. But anyway, so here's a natural standard Hamiltonian action on CM, and what we have is there is this A dual, right? It goes to G dual. Okay, and this is, maybe I should say, so from T dual there is this G dual. The map is given by A star, and the composition, let's denote it by mu G. So this map, the composition with this dual of the matrix A gives you a moment map of the restriction of the action of T to G. Yeah? So this is the moment map for G acting on CM. G is a subgroup of T. Yeah? So now what's the yeah, and then I want to talk about, so the toric manifold of O before we consider is a reduction of this CM by the action of G. CM, you reduce it by the group G. But then what's the regular value? The regular value I use is here you have eta vector, yeah, which gives you this the inequalities, right? And this element eta vector goes to A dual to eta. Okay, and this is going to be a regular value. So I'm gonna define our toric manifold and orbifold to be the reduction of the CM by G at the regular value A dual eta. Okay, and probably, so this is an exercise. Yeah. Okay, so what is this, right? What's the reduction space? You look at the preimage of the regular value. So the mu g inverse of the regular value. Yeah? And this regularity makes sure that the action of g on this preimage is locally free. So you have an orbifold in general. Right? And in the nice cases, of course, we sort of already know that if this delta is Delson polytope, unimodular polytope, and let's just say those labeling are all 1, and this is supposed to give you a toric manifold. So that means that in that case, for sure, G acts on this space freely. So you actually get the manifold. Okay? But I'm going to give you an exercise after I give you some tool, I give you an exercise saying that G acts on this preimage if and only if B equals 0 and delta is Delson polytope. And with the description I give you, it's not so difficult to show that this if and only if thing. This G acts on the preimage of the moment map freely if and only if delta is Delson. Yeah. Okay, so it's a big theorem, right? You restrict the standard simplex structure on this preimage, and it's normal symplectic structure because the dimension could be like odd dimension. But the degeneracy part, the degeneracy part of the restriction of the symplectic form here is exactly in the direction of that torus action. So if you quotient by that torus, it actually gives you non-degenerate simplex structure on the quotient. So that's the sort of morally what's happening in this reduction theory. Yeah? All right, so now Oh, this is bad. Huh? Okay, so now I want to understand this preimage of the regular value topologically or equivariant topologically. Yeah? And this is it's defined by some the quadratic equations. Right? This moment map, the standard one goes to square norms, and this is the linear map. And then you pick in some vector here, and then set them equal, right? And then find those z1 through zm. So it's basically given by, well, maybe I can just write down. So this thing is given by the equation A dual, and you multiply this thing and then set them equal to this vector. Yeah? So this is a bunch of quadratic equations, and what's the solution to this bunch of quadratic equations? And it's kind of hard to see at the moment what this is. But I'll tell you how you analyze this thing so that we can actually calculate cohomology of this or equivariant cohomology of this. Yeah? And that tells you the equivariant cohomology of the toric manifold or orbifold. Okay, so for that, we consider some affine embedding of delta. Yeah? So delta sits inside of R dual, which is Euclidean n space. Right? So now let's define this B tilde dual, which is a map from R dual to T dual. Okay? So R dual is really a map from a B dual is a map from R dual to T dual, right? As a linear map. But I'm going to define a affine embedding of this R dual to T dual. Since U to first send it by the matrix B dual, yeah? And then you shift it by this eta vector. Okay? So this is an affine embedding of Euclidean n space into M space. Yeah? And interesting thing is, what happens to the polytope when you apply this affine embedding? Yeah? So the image, let's say this is delta tilde. Yeah? So you send this polytope delta by this affine embedding. Yeah? And it's going to be, so it sits inside of T dual, and there is this first quadrant of the T dual. So all the positive, the coordinates of this part is all positive or non-negative. Yeah? And if you take an intersection with the image of R dual by this affine embedding, it exactly gives you the image of this delta. And it's kind of easy to see because so what does this linear inequality tells you about this image of U? Right? So B, so this part corresponds to B dual to U. Yeah? You take in the inner product between U and Bi times rho I. It's exactly the it's exactly ith row of this multiplication. Yeah? And then you're adding eta vector. Yeah? And it has to be, I mean, this notation is a little sloppy, but I guess you know what I'm saying. Right? And this is equal to 0. So the sum of them equals 0 exactly lands in the coordinate plane. Yeah? So that's how you see this equality. And so, I mean, you have to work it out also. So this is an exercise. But I'll show you this in the example, and it will be a little more clear. Okay, so from this computation, you can actually look at right. So the corollary from this exercise is, so now you have this, the pre-image, right? Yeah? And this is actually equal to, so here's the original picture of moment maps, right? So you have this, the regular value here, yeah? And it's the image of this eta. And now we have this delta tilde in here. Yeah? And delta tilde is exactly the kernel of, I mean, it's the pre-image of this over here. Not really. It's the intersection. So, okay. What is this? So that this positive first quadrant is the image of this Cm, right? And it's the intersection between the image of our dual in here, but that's actually the pre-image of this A dual eta by this map A star. Yeah? So the pre-image of this A dual A eta is exactly the pre-image of this delta tilde. Yeah? I mean, I was taking everything in the pre-image of this, but then somehow the image of this sits in the side of first quadrant, and you take a pre-image of this in here, but that's just a affine plane inside this, but you intersect it with the first quadrant, that will give you its pre-image here by this original moment map is exactly this level set. Yeah? Okay, so this is actually a nicer combinatorial and topological description of the space you're quotienting out. Okay?
B2 that's placed injectively. B2 that's power.
Yeah. Because this map is B was rank, full rank. So it's a surjective linear map. So if you take a dual, it's an injective linear map. And you're just shifting by some elements. So this is injective affine embedding. Yeah? So now, so I'm claiming this is a toric orbifold. I mean, in the symplectic sense. So there should be some moment map. So, but now it's general orbifold, so it's a little sloppy about like saying what the moment map is. But basically, the moment map for this toric orbifold is given by this map. So you have now you're taking a quotient. So this thing is a quotient of mu t inverse by delta tilde, right? And you're taking a quotient by G. So now you define a map. So this one, there is a restriction of this original moment map, and it lands in the image of R dual by this affine embedding. Yeah? And then because this B tilde star dual was affine embedding, you can actually pull back to the plane you're embedding. So you can actually use the inverse map here. So this actually gives you, so inside this you have this delta, and this is exactly the pre-image of this delta tilde, right? So the image of this lies in here, and if you pull back this delta tilde by B tilde star inverse, it exactly gives you the original delta inside of R dual. Yeah? So this is going to be the moment map on, this will induce a moment map on this toric manifold. So in the case when G acts on this freely, you actually get the symplectic manifold. This moment map, this mu R tilde actually factors through the symplectic manifold here, and it goes to R dual, and exactly the image is delta, and I should really denote this map as mu R because it's the R Hamiltonian moment map. Yeah? But somehow mu R tilde is a lifting to the space where you take before you take a quotient. Yeah? Okay, it's a little technical, so I have to give you example, and it's going to be a lot more clear. But before that, let me just state, well, maybe I should just start example first. Yeah? So the example, let's do a CP2. Okay? So here you have 0, 0, and 1, 0, and 0, 1. Okay? And let's say this is H1, H2, and H3. Okay? And you have this row 1, row 2, row 3. Okay? And here I want to get the toric manifold, so let's just put the labeling all 1. Okay? And this is supposed to be Delzon, right? Okay, so what is the matrix B? So you have row 1, row 2, row 3, 1, 0, 0, 1, minus 1, minus 1. Yeah? Okay? So, and also we need those eta to reduce the space. So let's write this polytope as an inequality. Yeah? Right? So to define this polytope, what's the half space given by this 1, 0 vector? This has to be greater than 0, right? Yeah? So row 1 is going here. It's everything above this coordinate plane. So there's nothing here. The eta 1 is 0. Yeah? And the second hyperplane is this x plane. Yeah? And it's also the standard half space, so it's greater than 0. Yeah? And you have minus 1, minus 1, right? What's the number here? 1 or minus 1? So this could be negative, right? Because it's the row 3 goes this way, but you're going a little backward. Yeah? So the intersection between u and minus 1 is going to be negative, so you have to add 1 to get positive. Yeah? It's 1. So here tells you eta is 0, 0, 1. Okay? Right, so right now, actually I want A, yeah, to write everything explicit. Yeah? So B, so you have this T, this is 3 torus going to 2 torus. It's given by this matrix B, right? So T1, T2, T3, that goes to, right? How do you read this, right? You have 2 rows. Yeah? You have to use rows, right, to get the 2 elements, the 2 torus elements. So you read first row, T1 and T3 inverse, yeah? And you read the second row, T2, T3 inverse. Yeah? And what's the kernel? Yeah. And the kernel should be diagonal, right? So somehow you look at the kernel of this matrix, that's 1, 1, 1. Yeah? So this is going to be just one torus sitting inside of T3 diagonally. Yeah? So maybe I should say a T goes to T, T, T. Yeah? That's A. So the matrix A, how do you write? That's going to be 1 by 3 matrix. Yeah? 1 by 3 matrix, 1, 1, 1. Yeah? And how do I know this is all the kernel? Yeah? I mean, I found the kernel of this linear map, but then when you calculate the kernel of the linear map, you're just looking at the kernel of linear map of R vector space.
Can't you just write down the equations, T1, T3, inverse to
Yeah, that's one possible way. Yes, of course, of course. But when this becomes really huge matrix, it's really hard to solve the equation in terms of torus. So that's why I gave you the exercise in the first place. If this matrix gives you a surjectional lattice, the solution to this equation is actually gives you the whole torus in the kernel, because you don't need to worry about the discreteness of the kernel. And this, how do I know this? The image of this from Z3 to Z2 is surjective. If you can make 1, 0, and 0, 1 by this image, then it's surjective, right? And 1, 0, 0 goes to 1, 0, and 0, 1, 0 goes to 0, 1. So this is certainly surjective map. Yeah. So you don't need to worry about discreteness of this. It's honest connected torus with the dimension, a codimension, right? 3 minus 2. Yeah. Okay. So now let's see what's happening with this affine embedding. All right, so what is this B tilde dual, right? So B tilde dual of U is defined by, so U sits in two-dimensional space, right? U, wait. So U is multiplied by the dual of B, so 1, 0, 0, 1, minus 1, minus 1, and you multiply U, and then you add eta, 0, 0, 1. Yeah? And let's look at the image of delta under this map, right? Yeah? So it's an image of convex polytope, so you just need to look at the vertices. Yeah? So let's look at, so this vertex, let's see, V1, 2. Yeah? We call it V1, 2 because it's an intersection between H1 and H2. Yeah? And this, say, V2, 3, this is V1, 3. Yeah? So V1, 2 goes to, V1, 2 is 0, 0, so this part is 0, you just get 0, 0, 1. So here is V1, 2. Yeah? And so this is 0, 0, 1. And V2, 3, it's 1, 0, right? 1, 0 goes to 1, 0, minus 1, and then you add 0, 0, 1, so you get 1, 0, 0. 1, 0, 0 is here, V2, 3. Yeah? And then V1, 3 is 0, 1 vector. So you have 0, 1, minus 1. You add 0, 0, 1. You get 0, 1, 0. Yeah, nice and pretty. Huh? So the convex polytope, convex hull of these vertices, it just gets this. So you see, as I said in more general setup, all the facets are given by coordinate planes. Yeah? It's not a coincidence. It happens all the time. That's what I was trying to say in this exercise. Yeah? Okay, so this is the delta mu. Yeah? And then here you have this moment map mu t. Yeah? Mu t is a map from Cm. So m is now 3. Yeah? And you have this z1, z2, z3 goes to z1 square, z2 square, z3 square. Yeah? So now it's really simple right now. Right? So let's look at the vertex. Right? So vertex is the intersection of two coordinate planes. So in this case, you have 0, 0, 1. Yeah? So you have two zeros and one non-zero. Right? When you have 0, the pre-image means that z1 equals 0, z2 equals 0. Yeah? And then here you have 1, z3 equal, square of z3 equal 1. So it's a circle. Yeah? So above this vertex, you have a circle. Yeah? And you're taking a quotient by torus, yeah? Diagonal torus. So it kills this circle, it gets a point. Yeah? And also, when you look at, say, so it happens to all these other vertices too. And when you look at this facet, right? So this facet is given by, so let's call this x1, x2, x3, the real coordinates. Right? So this facet is given by x2 equals 0. So it's given by z2 equals 0. Yeah? So if you go away from those two the vertices, right? First and third coordinates are non-zero, so it actually gives you a torus above this thing. Yeah? But then when you go to those vertex, one of the circle gets contracted. Yeah? And that you quotient by, so that's actually, so you have, so here you have torus and then you have a circle. And I think one of those the fundamental cycle is going to be contracted here. And this part above this line, it's going to be S3. Yeah? And then if you take a quotient by diagonal action, it gives you one of the torus over here, and it gets CP1. Yeah? So it's, all I'm saying is when you pull back this description of the preimage of the moment map to this embedded, affine embedded polytope in this three-dimensional space, the equivariant structure is more clear. Yeah? So that's my sort of punchline here. And then actually, I want to explain better theorem, but before that theorem, I will give you some notations. Yeah? So this is about topological or combinatorial model for mu inverse t of delta theta. Yeah? So we needed this preimage of delta tilde by this moment map mu t to get symplectic structure. But if you don't care about the symplectic structure or the smooth structure even, as a just topological space, there is better description of this space. Yeah? So first, I have to define what the simplicia complex associated to a polytope. Everybody's okay with the simplicia complex? Yeah? So delta is polytope. I have to say it's a simple polytope. Then K delta, it's a simplicia complex so say there are m facets of simple polytope, and what is this simplicia complex associated to this delta? And it's a simplicia complex on the vertex set M, 1 through M. So basically, the vertex of this simplicia complex is exactly the facets. Yeah? And sigma is an element of the simplicia complex if and only if. So, by the way, simplicia complex on a vertex set 1 through M is really in the power set of this set 1 through M. So it's a subset of all the subsets of collection of subsets of M. Yeah? That's the where this simplicia complex sits. Yeah? So sigma is in this simplicia complex if and only if H intersection of the facets are not empty. Yeah? So maybe I'll just do an example. Let's say it's a polytope, right? H1, H2, H3, like we have over there. And what's the simplicia complex? So it's a collection of subsets. Empty set is there, okay? And 1 is there because H1 there's nothing to intersect. It's there, and 1, 2, 3, they're all there. And what about 1, 2? 1, 2, H1 intersect H2. There is a vertex here, so intersection is non-empty. So there is 1, 2 set. And 2, 3, there is also intersection. And there is also 1, 3. Intersection is a vertex. Yeah? But then, what about 1, 2, 3? Yeah, intersection of H1, H2, A3 is empty. So in this simplicial complex, 1, 2, 3 is not there. Yeah? And as a picture, you actually can do like, you have 1 and you have 2, you have 3, yeah? And then there's a 1, 2 edge, right? H1, H2 intersect, 2, 3 edge, and 1, 3 edge. Yeah? So the simplicial complex geometrization looks like this. Yeah? So I have like 10 minutes more. Yeah? Okay, so now I introduce this topological or combinatorial model for this moment map image to get the toric manifold. It's called the moment angle complex. So this actually defined for any simplicial complex. Yeah? And it's denoted by ZK. Yeah? And it's defined as the union of the products of disk and circles. So let's say D. D is the unit disk, yeah, in complex plane. And the boundary is the circle, the unit circle. Yeah. So for each phase of the simplicial complex, you take some disk and circle products. When you have, so I denote this way. Yeah? I think it's very convenient notation, but maybe people don't like this. So what does this mean? So it's inside of CM. Okay? And for the first, say, the first component of this CM, if this 1 is an element of sigma, you put disk. If 2 is in sigma, you put disk. But if 3 is not in sigma, you put circle. Yeah? So whenever the index inside of sigma, you put disk. And whenever you don't have that index in that sigma, you put the circle. Yeah? So this is the notation. Yeah? Let's do an example. Yeah, let's do that for here.
What is writing how?
This, yeah. So M is the vertex set. Yeah? It's a complement of sigma. It's a complement of sigma. Yeah? So what is Z of this 1, 2, 3? Yeah? So first, let's look at the 1, 2 edge. Yeah? So 1, 2 edge, you have disk, disk, and third component is circle. Yeah? Disk, disk, circle. Yeah? And you have 1, 3, disk, circle, disk. Yeah? And then you have T 2, 3, circle, disk, and disk. Yeah? And the union of these. Okay. And why don't I care about smaller faces? Yeah? So a priori, this definition says you take all the faces, like you look at all the elements, and then you look at this thing. Yeah? But then simplicial complex by definition, when you take a facet, the maximal face, all the subsets of that is sitting there. And once you take all, so for example, if you take 1, that's D cross S1 cross S1. Yeah? But this thing is contained in this and this. So you don't actually need to take a union of this. You just look at all the maximal faces. Yeah, that's enough to take this union. Yeah? And I think if you are expert in homotopy theory or something, the classic homotopy theory, and this is homeomorphic to S5. It's not easy to see. I guess not. Oh, sorry. Yeah. Okay. All right. So the theorem is So this looks very like combinatorially, topologically simple space.
S5 for each one or for three?
The union of these things, S5. Yeah, so this thing is S5. Yeah, it's hard to see.
If you take the first two ones, this is S3 times D3. And you can conclude that.
Yeah, so like he's an expert, yeah. But I don't know how to actually get this, but I know from this theorem. Yeah. So the theorem is there exists Tm equivalent homeomorphism between this preimage. Yeah. So this is the space you want to quotient to get a toric manifold to zk delta. Yeah. So here it's really hard to see how the space looks like and how the torus acts on it. Well, but it's sort of getting clear once you write this, over this you have this C, and somehow it's a torus bundle degenerate on the faces. Yeah? But more combinatorially, we can write it this way. But you forget all the smooth structures. It's a topological homeomorphic only. Yeah, but if you want to calculate the equivariant cohomology, this is very enough. And then I'll convince you by proving the cohomology of this is something called a Stanley-Reisner ring. Yeah? Okay, the idea of proving this is not so bad. So now you're looking at the preimage of this delta tilde, right? In this C, right? So now let's look at the unit cube. Unit cube, I should write it as this is this. Okay? And then I'll do something weird. So I decompose this polytope into 3 pieces. So it's kind of subdivision. Yeah? Take some point here and then divide it into 3 pieces. Yeah? Say this is delta 1, 2. No, this is 1, 3. No, this is 1, 2. And this is delta 2, 3. And this is delta 1, 3. Yeah? So now you sort of shuffle this around, and it's continuously like push this to the boundary of this cube. Yeah? Without sort of changing the face structure much. And it becomes, maybe I should write it over here. So it becomes this, this, and this. So this is, let's say, after you push forward in this direction of this delta tilde, it becomes 1, 3, and delta 2, 3. Yeah? And without changing like structure of the vibration here. Yeah? Like I didn't really change this vertex, right? But even if this vertex was pushed a little this way, but you can just bring it back to the unit coordinate here, right? So that all the vertex are those vertex, and then you're bringing this part is over here, but the difference between this and this, there's nothing in the vibration. It's anyway torus, right? So this line continuously moved to this, yeah? And this line continuously moved to this, and this line continuously moved to this, yeah? Without changing the vibration. Yeah? Of course, this is going to be not smooth, but continuously. Yeah? And then this membrane becomes attached to the boundary of this cube. Yeah? So now, so mu inverse T of delta 2, 3. Let's look at this. Yeah? Yeah. So I should use this delta tilde, right? Because it's different from the original part of the polytope, right? And it should be homeomorphic to this, yeah? And when you look at this, this is exactly, I picked 2, 3, right? It's going to be exactly this. Yeah? So once you push this polytope to the boundary of the cubic, and then each piece corresponds to one of these things. That's how you prove this theorem. Yeah.
Was the theorem as a Buchstabe?
Yeah, exactly. So this theorem is due to Panoff and Buchstabe. But somehow, this space was already known in Danilov and Davis and Januszkiewicz's paper. They constructed this space without having this circle decomposition. But this circle decomposition was done by Panoff and Buchstabe. And the reason why they constructed this so-called moment angle complex or moment angle manifold is that they wanted to generalize toric manifold to something called quasi-toric manifold. Yeah. Okay, so next lecture I'm going to calculate the equivalent cohomology of toric manifold or the moment angle complex purely topologically using this description. And then hopefully I get to ordinary cohomology too.